Hello viewers. Unlike conventional electronic devices or unlike semiconductor physics, in bioelectronics, semiconductor materials and also biological materials both have equal importance. Because bioelectronics is basically a cross-fertilization between semiconductor materials and biological materials. So, as far as cross-fertilization is concerned, both materials are supposed to have some sort of analogy. So in this lecture, my basic objective is that how to transform the intrinsic and extrinsic concept available in semiconductor materials towards the biological material. And as far as biological materials are concerned, the typical habitat of biological systems, as you all know, that is made of electrolyte solutions, that is water solutions containing ions and solutes. And in such a medium or in such biological system, as far as one single molecule is concerned, that is suppose for example one water molecule, we know that two hydrogen atoms and one oxygen atom combine to form a water molecule with covalent bond. And it is basically a dipole. Whereas in a bulk water solution, one water molecule binds with another water molecule through dipole-dipole interaction, which is a type of physical bond, commonly known as hydrogen bonds. And in physical bonds such as ionic bonds, unlike covalent bond, here an electron is completely transferred from one atom to another atom of a different element, forming charged particles called ions. Such bonds are formed between highly electronegative, that is electron accepting, and highly electropositive, that is electron donating elements. For example, in the formation of a bond between sodium and chlorine, the sodium atom loses an electron and becomes a sodium ion, and chlorine atom gains one electron and becomes a chloride ion. The resulting ions exert an electrostatic attraction and enter into a bond formation. So from this it is obvious that in biological medium we may get different types of bonds. For example, we may get covalent bond, that is for example bond between hydrogen and oxygen in one water molecule. Ion-ion interactions, for example, suppose sodium chloride, which is a physical bond. Ion-dipole interaction, say for example one sodium ion and water dipole, which is also a physical bond. Dipole-dipole interaction, for example, suppose attraction between one water dipole with another water dipole, which is also a physical bond. So from a technical point of view or engineering point of view, the interaction energy of these different bonds and a mathematical expression is required. Say for example, in case of ion-ion interaction energy is given by this equation 3.1. ER equal to minus Z1 Z2 Q square divided by 4 pi epsilon naught epsilon r capital R, where Q is equal to ZQ. Z is the valency of the ion carrying elementary charge Q. Epsilon naught is the permittivity of vacuum, and epsilon r is the relative permittivity of the medium. Capital R is the distance between the two charges Z1Q and Z2Q. And in case of ion-dipole interaction, this interaction energy also can be deduced utilizing Coulomb's law and given by expression 3.2. Figure depicts interaction between an ion and a dipole denoted by U. Also, in case of dipole-dipole interaction, this also can be determined and approximately it can be shown as given in equation 3.3. Here 2 point dipoles of moment U1 and U2 at a distance capital R is shown in the figure, where interaction energy, which is a function of distance between the dipoles, their angles, is given in equation 3.3. Some problems are also given here, say some problem 3.1 and from problem 3.2, both can be solved using equation 3.2. And let us see intrinsic and extrinsic semiconductors, that extrinsic materials that we have discussed in case of semiconductor materials. How can we apply this concept, intrinsic and extrinsic, in biological medium? For this, let us first consider one water medium and also assume that at room temperature, a small fraction of these dipolar molecules be thermally ionized according to the generation recombination scheme given by equation 3.4. That is, water is dissociated to hydrogen ion and hydroxyl ions, where of course square brackets indicate concentrations, that is molarity. And if this scheme, chemical scheme, is such that under standard conditions, the concentration multiplication of hydrogen ion and hydroxyl ion is equal to 10 to the power minus 14 mole square. That is, hydrogen ion concentration equal to hydroxyl ion concentration equal to 10 to the power minus 7 mole. Then this, if it happens, then that medium is regarded as the intrinsic biological medium. And if we express it in logarithmic form, then it will be minus log 10 minus log hydrogen ion concentration to the base 10 equal to 7, or simply it is written as pH equal to 7, where pH equal to negative log of hydrogen ion concentration to the base 10. So, such an intrinsic biological medium can be made extrinsic by adding acid or base to the intrinsic biological medium. It is because acid is a substance that donates protons and base is a substance that accepts protons. So for one example, if we want to give a simple example, it will clear you. For example, suppose we want to find the pH of a Y mole solution of hydrochloric acid. How can we do this? So Y mole of hydrochloric acid solution, that is, how can we prepare? It is prepared by adding Y moles hydrochloric acid per liter of intrinsic water medium. Therefore, intrinsic concentration will be 10 to the power minus 7, which is analogous to Ni of semiconductor material discussed earlier. And due to addition of acid, the hydrogen ion concentration, that is H plus, will then shift to a new value. Say suppose example, it becomes X. Thus, proceeding exactly like p-type semiconductor, we get the following quadratic equation, equation 3.7, x square minus yx minus 10 to the power minus 14 equal to 0. Now solving for x equal to h plus, we get x equal to y by 2 plus y square by 4 plus 10 to the power minus 14 root over. This is equation 3.8. And after, since x equal to hydrogen ion concentration, so pH of the solution, now after getting this value, pH of the solution can be obtained by using equation 3.6. Now suppose we want to find the pH of a Y mole solution of potassium hydroxide. So potassium hydroxide solution, basically a basic solution. So it will be related with hydroxyl ion concentration. So such a solution is prepared by adding Y moles potassium hydroxide per liter of intrinsic water medium. Therefore, intrinsic concentration is 10 to the power minus 7, and due to addition of base, the hydroxyl ion concentration will shift to a new value, say Z. Thus, proceeding exactly like N-type semiconductor that we have discussed earlier, we get the following quadratic equation, that is Z square minus YZ minus 10 to the power minus 14 equal to 0. Now solving for Z, we will get the equation 3.10, from where we get the value Z, where Z is the hydroxyl ion concentration. So to find the pH value of the solution, we have to determine first the hydrogen ion concentration. After getting the hydroxyl ion concentration, we get the value of hydrogen ion concentration utilizing equation 3.11, which is hydrogen ion concentration into hydroxyl ion concentration equal to 10 to the power minus 14. From this, Z is here Z is known, which will be given by equation 3.10. So hydrogen ion concentration can be determined. After getting this, pH value can be determined. So this is the basic concept. How can we transform the concept of intrinsic and extrinsic, very commonly used in semiconductors. How can we transform this concept towards the biological material? Essential, because main objective is to find some sort of analogy between the semiconductor material and biological material. And if we observe from here, from this discussion we have observed that certainly the intrinsic and extrinsic concept can also be explored in biological material, and as a result there is certainly possibility of interfacing biological material with semiconductor material. A very essential step required for at least for fabrication or for construction of some sort of bioelectronic devices. And some examples, problems are given. Say, for example, find the pH of a 10 to the power minus 8 mole solution of hydrochloric acid, exploring the concept of intrinsic and extrinsic biological materials. So directly utilizing equation 3.7, you will get the value of hydrogen ion concentration X equal to hydrogen ion concentration, and after this you will get the value of pH utilizing the basic pH definition. And also suppose 10 to the power minus 8 mole solution of potassium hydroxide solution, what is the pH value? Then for that you have to use the equation 3.10 and 3.11. Utilizing this, you will get the pH value of 10 to the power minus 8 mole solution of potassium hydroxide. Similarly, problem 3, pH of arterial blood is measured by pH electrode and found to be 7.4. Suppose, what is the hydrogen ion concentration of arterial blood? Then you use the formula, pH definition. And as far as biological materials are concerned, which are extensively used in bioelectricity, mostly used in suppose biosensor development. These are mainly proteins, deoxyribonucleic acid, DNA, ribonucleic acid, RNA, cell membrane, eukaryotic cell, enzyme, antibody, antigens, etc. You will little bit of knowledge on these materials are required, that you will certainly get some textbook of microbiology. And also, as far as solutions are concerned, one of the important solutions which is frequently used in bioelectronics or biotechnology laboratories are pH buffer solution. pH buffer is essentially a substance or a mixture of substance that allows a solution to maintain a near constant pH even upon the addition of a small amount of hydrogen ion or hydroxide ions to it. Because in most cases, as far as measurement is concerned, analytical measurement, the pH must be kept at a constant value. For that, this type of buffer solution will be required. Conjugate acid, suppose weak acid such as acetic acid, and conjugate base such as weak base such as amines can form pH buffer solutions. As far as biological side is concerned, amino acids and proteins are examples of biological buffers. And also one very important term which is frequently used in laboratory, the ionic strength. Ionic strength of an electrolyte solution is defined by a mathematical expression I equal to this, half summation of multiplication of all concentration and valencies of respective ions, where Ci is the concentration of the ith ion, Zi is the valency, and the summation extends over all the ions in the solution. It is from here the obvious that the Ionic strength is a property of the solution and is not the property of any particular ion in the solution. Only the net charge of an ion is used in calculating ionic strength. As a matter of fact, unionized compounds such as weak acid or a dipole compound does not contribute toward the ionic strength of a solution. So with this, I conclude my lecture. Thank you.